Okay, so now we're going to go on. So we've been simplifying radicals, right? So we've taken these quantities, these radicands, and we've either factored them using perfect squares, or we've used prime factorization to figure out how to simplify them. So now we're going to apply that to adding and subtracting radical expressions. Meaning, we're just going to take radicals, one radical, and add it to another radical, or subtract radicals. Now, in order to do this, we have to kind of embrace this idea of like radicals. And I think of like radicals, basically they're the same thing as like terms. Right? A like term has to have exactly the same variable, so a like radical has to have exactly the same radicand. And remember, the radicand is just the number underneath the radical sign. So they have to have exactly the same radicand. So, let's talk examples versus non-examples. Just to give us a little bit of an idea. So examples would be 4 radical x and negative 10 radical x. Those are exactly the same radicand, so they could be combined. I could do 4 minus 10 to get negative 6 radical x. The radicals do not change. The coefficients, the numbers in front of, not the index, right, but the coefficient, the number in front of, does. So 3 radical 6y and 1/2 radical 6y. Exactly the same radicands. So let's talk non-examples. Things that easily confuse us. Non-examples would be 2 radical 8 and 8 radical 2. They have the same numbers in the problems, but their radicands are different. I have a radical 8 and I have a radical 2. They cannot be combined. They stay separate. Negative 6 radical x and radical 6x. Their radicands are different, right? This radicand is x. This radicand is 6x. They cannot go together. 4 radical 8 and 4 cube root 8, right? Those are different. Mainly because this radicand, right, this radical it has an index, and this one does not have an index. This index is 2, this index is 3. We're not going to put them together to make it a little bit easier on ourselves. They'd stay separate. So if you can embrace this idea of like radicals, like terms, there are 2 types of problems. Type 1 is the easiest. If the radicands are the same. So if the radicands are the same, add or subtract the coefficients. If the radicands are the same, you just do the math. You add or subtract the coefficients, and voila, you're done. If the radicands are the same. So let's practice a little bit. 3 radical 7 plus 8 radical 7. Are the radicands the same? Sure are. So 3 plus 8 is 11 radical 7, and you're done. Try a little bit harder. So 9 radical y minus radical y. Now, lots of people are going to go too fast on this one. They're going to say, oh, Mrs. Long, that's easy. The answer is 9. 9 radical y minus radical y. The radical y's disappear. No. Because this is 9 radical y's. 9 radical y, 9 radical, right? Radical y, radical y, radical y, radical y, 9 times. That's how you have to think of it. So this is really 1 radical y. You have to put that coefficient in there. So 9 minus 1 is 8, and the radicand stays radical y. 1 radical 4 minus 4 radical 6. Do those have the same radicand? No. Let's change that 4 because that's an ugly number. Let's change it to 8. By ugly number, I mean it works, so my problem's wrong. That just doesn't work. So that's the final answer. Now, before you get super excited and say, oh, sweet, so it's just can you or can't you? You have to then simplify. So this type right here, where the radicands are not the same, the radicands are different, this problem leads to type 2. Let's change color to type 2. This problem leads to type 2. So sometimes you need to simplify. The radicals. Then add or subtract. So sometimes you have to simplify first. In fact, most of the time you have to simplify first. So if I had radical 12 plus radical 27, I'm going to look. They don't go together. They're obviously not like radicals. So I'm going to look, can I simplify? So I'm going to go to 12. I could do 2 and 6, or I could do 3 and 4. I'm going to pick 3 and 4 because 4 is perfect. So I'm going to do 3, and I'm going to do 4. I draw a box around the 4 because it's a perfect square. I circle the 3 because it stays behind. I'm going to do the same thing with 27. 27 is 3 and 9. 3 and 9. I draw a circle around 3 because it's prime, it stays. Draw a box around 9 because it's a perfect square. Remember, when we learned this, you could still factor 4 into 2 and 2, and it makes a pair. And you take one of the pairs out, or just stop at perfect squares. Perfect squares, you can do the square root of. So the square root of 4 is 2. What stays behind is what's circled, the prime number 3. The square root of 9 is 3. What stays behind is 3. Now I have the same radicand, so I can add my coefficients, because this is an addition problem. 5 radical 3. Okay, so let's try 5 radical 28x plus 8 radical 7x. So again, I'm going to look at 28, which is 2 and 14, or 4 and 7. I'm going to pick 4 and 7 because 4 is perfect. 4 and 7, draw a square around the 4, circle the 7. There's also a lonely little no exponent variable. So the square root of 4 is 2, so 2 is going to come in front, so that means it's 5 times 2, and what's left behind is radical 7, plus, can 7 be factored? No. So this stays. 5 times 2 is 10. 10 radical 7 plus 8 radical 7 is 18 radical 7. Okay, let's try this one. Radical 48 x to the third plus radical 12 x to the seventh. All right, so 48, if I look at my factor squares, I have 48. I can do 2 and 24, 3 and 16. Ooh, 16s are perfect. Let's see if there's anything else. 4 and 12. 4 is also perfect, but I'm going to go with 16 because it's a bigger perfect square than 4. And 6 and 8. Okay, so 3 times 16. I have an odd exponent, so I'm going to take 1 out. So circle 3 because it's prime. Draw a square around 16 because I can do that. Circle x, draw a square around x squared. So 16, the square root of 16 is 4. The square root of x squared is x. What's left behind is 3x. 12 is 3 and 4, so 3, 4. X to the 7th, I'm going to take out an x and leave x to the 6th. Circle, perfect. Square root of 4 is 2. I divide my exponent by 2, so 6 divided by 2 is 3. And I'm left with 3x. Now there's my question, can you add these together? Can you do 4x plus 2x to the third? The answer is no. Because not only do the radicands have to be like terms, right? The coefficients must also be like terms. So the answer to this problem is 4x radical 3x plus 2x to the third radical 3x. They cannot be combined because they're not like terms. So the coefficients also have to be like terms. All right, so let's try a big numbered one. Let's just, show that we can do it. So if I gave you radical 32 plus radical 128. 32 is pretty easy to simplify because it's on my factor square. So I go to 32. I could do 8 and 4 because 4 is perfect, but I want to do 2 and 16 because 16 is the bigger perfect square, right? So I'm going to do 2 times 16. Draw a box and circle it. So this guy right here is 4 radical 2. 128 is harder. I don't know the factors of 128 off the top of my head, so I'm going to go long way around. I'm going to factor it kind of to the side so that we can have some room. Okay, so 128, it's even, so I'm going to divide by 2. So 128 divided by 2, well, 12 divided by 2 is 6. And 8 divided by 2 is 4. Prime. And this just happens to be perfect. So the answer is 8 radical 2. So now can I add them together? Yeah. 12 radical 2. So just because that number is big doesn't mean it's automatically terrifying. typically what's going to happen when we're working with problems like this number right here is going to have the radicand from the easier one as its radicand over here. So like just divide by that leftover number and see if it works. If it doesn't, you may have to do a little bit more math, and that's okay. But just because these numbers are big, don't freak out. Like it's probably easier than you think.